everyone. Welcome to Hands-on AI, where we walk you through AI lab step by step. I'm Annie.
And I'm Ayo.
So yesterday, Ayo, what did we talk about?
So yesterday we learned how can you do extraction, transformation, and loading of your data, leveraging the power of BigQuery and Gemini. So we learned how can you use something like ML generate text, which is a command in BigQuery, to call Gemini, convert your unstructured data to JSON, convert those into smaller tables, and then do general structured analytics against it. So SQL analytics, ranking. So essentially getting insights from your data. So really powerful techniques.
Yeah, and we're also gonna cover a little bit of retrieval augmented generation in BigQuery, and also like RAG retrieval augmented generation in CloudSQL for today's lab. So today we're gonna build a RAG agent with CloudSQL and ADK. And by the end of today's episode, you're also gonna find a boss, right?
Yeah.
Okay, so since we already redeemed the credit last episode, if you haven't redeemed the credit and if you don't know what is a lab, making sure you check the last episode. And today, let's continue with our BigQuery analytical data and our RAG with CloudSQL. So I'm going to start with the RAG in BigQuery first. Let me share my screen. Right? Okay, before we start to do the RAG in BigQuery, Ayo, let's go through what are retrieval augmented generation, right? So retrieval augmented.
Oh. Yeah, go ahead. Yeah, what's retrieval augmented generation?
Retrieval augmented generation basically, my understanding is it's trying to solve the hallucination of AI. Because AI is not always give you the accurate result, doesn't necessarily have the specialized knowledge. So that's why we want to have a personal database. We have a specialized database to AI, so that first we want to do the retrieval from that database. And then we want to, once we have the result from the retrieval, we want to augment the result from the retrieval to our existing knowledge base. And with that, we generate the final result. And for this whole process, we want to retrieve from a vector database. That means we want to get embedding from the things we want to query from, and then we want to query from embedding space to do all the retrieval. So why don't you explain us in this diagram, we have this chunking and embedding. What does that mean? Because I know the retrieval augmented generation, but why we have chunking part here?
Yeah, great question. So there's multiple techniques behind retrieval augmented generation and reasons behind it. So when you're working with these big unstructured documents, it could be text files, it could be PDFs. It doesn't make sense for various reasons to try to embed the entire document at once. First and foremost, there's kind of like the semantic encoding that you're trying to accomplish with something like retrieval augmented generation. You want to make sure that you're encoding the document in meaningful chunks so that when you do the retrieval part, essentially you're retrieving aspects of the document that most directly aligns with that particular question or statement. If you encode everything at once, you can kind of dilute the semantic meaning of what's being encoded. So you want to make sure that whether it be paragraphs, whether it be sentences, whatever method you choose, that you're encoding it in a way where you're encoding meaningful blocks of the document. So there's different techniques. So there's fixed length, there's recursive chunking, there's content aware. So you're using something like Google Cloud's document AI. It allows you to essentially grab paragraphs at a time from a document. So that's a useful way of essentially capturing the semantic boundaries of a unstructured, text. So that's essentially what we mean by chunking. And then when you're doing the embedding, there's different embedding models. There's one that actually just released earlier this month. I believe it's called Gemini Multimodal Embedding 2. Essentially, it allows you to embed multimodal data. It could be audio, it could be PDFs, it could be text files. But ultimately, what you're doing is you're converting this into multi-dimensional vectors that essentially allows you to do things like vector search, where essentially you kind of do nearest neighbor matching, which we're going to talk about very soon.
Yeah, so I just showed our latest Gemini embedding 2. Basically, we can get this numeric representation of all different type of data, including like video, image, video, text, image, video, audio, and document. That's pretty cool. And in today's lab, we're going to talk about how to do the recursive chunking, and then using embedding in BigQuery to get the embedding from the things we want to query from, and then we start to do our RAG. So when we try to calculate the distance, I know that we have different way of understanding how close they are in the embedding space. So the different approach, like cosine distance and Euclidean distance, right?
Yeah, exactly. So essentially all we're doing here is, so again, when you're doing something like retrieval augmented generation, you have a knowledge base of essentially embedded knowledge that you've pre-embedded. And then when you have a question that's useful, like what is the date this contract was signed? Imagine like a legal use case. You want to be able to embed that question, and then you then do nearest neighbor matching between that embedded question and the knowledge storage that you have of embedded, information. And essentially, there's different ways of essentially finding which information that's been pre-embedded most closely matches with that question. So there's cosine distance you can use, there's Euclidean distance, but overall, we always recommend something like cosine distance because it's more of a matter of like the similarity rather than just like the magnitude. So something like Euclidean distance would factor in magnitude. What we mean by that is like the length of the document, things like that. But oftentimes what we care about is how similar are they rather than, how big is the context.
Yeah. I know some of use case also using sine, but I think I see cosine more often in the embedding. But let's get started with how to do that in BigQuery. Yeah, so currently we are at step 5. So if you're curious about how we do the extraction, loading, and transformation, making sure you're checking our last episode, which we cover all of them. So let's continue and actually start by how to do the recursive chunking and getting the embedding and do the similarity search in BigQuery. Right, so this is the first query we want to copy to the BigQuery Studio. So currently, I'm copying this command and then I'm this query and going to console.cloud.com at BigQuery, right? So I'm at the studio. Right hand side, I have this new empty query. So I just paste it over here and click run. And while we're waiting for the result, it's already creating the result for us. We can see that it's already created the chunked table for us. We have this job information, the result.
Yeah. And also just to clarify one thing that Annie mentioned. So yeah, in the previous day, yesterday, we covered extraction transformation of loading data with BigQuery, but that was in one context, going from unstructured to structured. Even as part of RAG, as we just kind of covered, there's some sort of transformation involved as well. So you're converting the documents into embedding. So that's the sort of transformation. But essentially, there's two different types of transformations that we're learning. One with ML generated text for JSON, encoding, another one for like ML generated embedding for embedding encoding. So there's different ways of kind of transforming your data in BigQuery.
Yep. And now you can see we got this chunk. Remember, we're using, let's see what are the things we copy. We're using the recursive chunk to chunk the data first before we get the embedding, right? And here, this is a result of the chunked text, but this is still it's unstructured data, and we still need to get the embedding representation of this chunk data.
As you mentioned, we're doing recursive, and pretty much as you can see in the query here, essentially we're just chunking the input data along each period. So this is what you would call perhaps not context aware. So you can imagine there might be meaningful context that's along multiple periods or multiple sentences, but overall all we're doing here is kind of like a blind raw. Every sentence is going to be its own chunk, essentially.
All right. So now we know what are the chunks. Let's try to get the embedding model and convert them to embedding. So first, you need to check the connection. Let's just copy this and go to our Google Cloud Console and just trying to echo this existing GCS connection and making sure we have the valid project ID and region set up. You can see that now we have a valid GCS connection here. Ayo, what is this GCS connection and why this is important?
Yeah, so as we kind of covered in day one yesterday, just remember that in Google Cloud, most operations have some sort of identity. So whether it be a service or the connection between two different services, you have to have an identity behind that. So in day one, we created this connection that kind of served as the connection identity between Gemini and BigQuery, as well as GPS and BigQuery. Now what we're going to be doing is create a connection between our embedding model and BigQuery. So essentially, you have to have some sort of connection identity, and we just established what it was. And now we're going to go ahead and create the identity or create the connection.
Yeah, so here, this is a model we're trying to use, right? This is a text embedding model, not our latest Gemini model. But here, this is a connection. We need to create a connection between the text embedding model with BigQuery. And here, remember, this is a placeholder text. You cannot just run directly with this one. You have to replace this with a real connection, which I will just explain to you. So I just copy this and go to my, I'm going to close this, go to my BigQuery studio. And in the query over here, I'm going to open a new query. I'm going to paste it. Remember, don't click run right away. You need to replace this with a real connection. So I'm coming back to this. I'm going to copy this connection and replace this so that we create a connection between the embedding model to BigQuery. And now you can see that you just create an embedding. I think, the error just saw should be you can ignore that.
Yeah.
And now you can say successfully create this text embedding model.
Yeah. And one thing to notice as well, we're not using the Gemini embedding 2 model that we talked about earlier. We're using kind of an older version, but for our lab, this is more than good enough. We don't really need multimodal embeddings because we're just working with text data. So we're just going to be using the text embedding Python model.
Yeah. And next, let's try to use ML generate to using this embedding model and convert our unstructured data to structured data with this text embedding model. So here we're using ML generate embedding. Remember, this is what we mentioned last time, that here this is the way we're using AI in BigQuery, that we have this ML generate embedding. And then the model is the model we're going to use, and we have a prompt that the data has to be converted, and a struct is a model parameter. So this is the way we're using ML generate embedding. And let's just copy this to our query. So I'm going to replace the last one. So here we are actually selecting, we are actually from this chunked data and selecting those using our embedding model.
Yeah. Yeah. So just iterating through the chunk data that we created earlier and creating an embedding for each chunk. Yeah.
And this is exactly also the format we just mentioned in the slide, that we have this ML generate with the model. Struct is the struct is our parameter, model parameter, and with our prompt over here. And let's see what does the result look like.
So since we're calling the embedding model behind the scenes, it may take some time just because there's an actual API call behind the scenes. So so BigQuery does automate a lot of the parallel application across multiple chunks at a time. But since we are calling the API behind the scenes, there will be a little bit of latency, but overall it'll be pretty quick.
Yeah, and we can see the extraction graph over here. It says query completed. Let's take a look at this. I'm gonna zoom out so that you can see this. Can you see this?
Yes. Yeah.
Yeah. As you can see that, we can see the execution graph over here with the query we just mentioned over here. And once you complete, and let's try to inspect the table to see the actual semantic fingerprints. So just copy this, and we can open a new query, and let's take a look. So finally, we see those ML generated embedding over here. So this is not unstructured data anymore. For all the chunk data, we are getting this embedding data from the chunk data, unstructured data, right?
Yep.
Oh, another thing that I just mentioned, you mentioned that we're using the model here, but we're not actually loading the whole model. We're actually pointing to the virtual. We have a pointer point to the model in Vortex AI, right? With ML generate.
Exactly. So behind the scenes, ML generated embedding essentially handles and manages that connection with Vertex AI behind the scenes.
Yeah.
And again, at the end of the day, all we're doing is creating an embedding, which is like a multi-dimensional vector. So I believe,
as you can see,
text. I believe text embedding 5 is 768. Let me double check.
Yeah, I think it's 768 dimension. So basically, we have 768 dimension perspective to describe a text information.
Yeah.
And next is, let's do a semantic search with BQML. So semantic search, we also covered before that we want to get an embedding of the things we want to query from. And then we want to, like, in the embedding space, we either using call sign or Euclid, or what is that? How to say, this is like Euclidean. Thank you. Euclidean distance to calculate how close they are in the embedding space to see how similar they are for the meaning, right? For the things you want to query from to the whole embedding space. And here we are using cosine to find the top 3 result that's actually close to things we want to query from. So I'm going to copy this. And here we're also going to use ML generate embedding. And also here's ML generate embedding with a model. It's similar text embedding model. Strong is things. And here this is the prompt you want to send to the model to get the embedding. And here you're trying to do the vector search with cosine and get a top 3 result to get the similarity search result. So this is the retrieval part of our retrieval augmented generation process.
Yep. Just
copy this and paste it and replace.
Yeah, so it's earlier. Yeah, so the reason why the benefits of retrieval augmented generation is because without retrieval augmented generation, the model oftentimes is limited to its pre-trained knowledge. So it may not have knowledge of your unique business, documents, or it may have knowledge of real-world information. But you can use things such as retrieval. Then you augment it. So now the model has at least that as grounding that it can use for, new information and grounded information and grounded responses.
Yeah. Example can be, for example, what is the latest Pixel phone? And if we don't have that latest information in our knowledge from the model side, you can have that information in the database, and then we retrieve from that external database to get the latest Pixel model, and then you augment this result to the existing model knowledge, and you generate a result that's more accurate and more latest.
Exactly. Yeah.
So here you can see that we get this distance, and the closer they are usually means the similar they are to the things that we want to search from. And here, because previously we set a k equal to 3, we want to only get the top 3 result. So you only see the 3 result over here. And they actually rank by the distance. And this one should be the most similar to the things you want to search from. Right?
Exactly. Yeah, so you're expecting that top response to be the most similar to the underlying question. So what was our question again? What are the tactics against a foe that causes paralysis? As you can see in that top matching response, you can actually see the exact word, paralyzing aura. So in a way where you can kind of see the semantic meaning is pretty much captured within that response. And that's exactly what you would expect. And again, the benefits of something like this is what we learned in day 1 yesterday was how can you do structured analytics with unstructured data. And that's very useful for very, very many different use cases. But oftentimes there's certain things you cannot convert into structured queries. So yes, I can answer, what were the top 3 monsters that were fought by this particular, warrior. Those are things you can do with ranking with SQL. When it comes to things that have semantic meaning involved, embeddings, retrieval augmented generation is your best bet of actually kind of getting useful insights.
Yeah. Thanks for the explanation. And that's it for RAG in BigQuery. We just finished step 5, and let's continue to do our CloudSQL part. Yeah, all right. If you take a look at the slide, that our biggest challenge so far is we want to processing this unstructured data, right? So previously, we for the last episode and what we just covered so far is what we call OLAP string. So this is for analytical processing. It's processing massive, clean, structured data so that we can do it for training new model or fine-tune existing one, right? But the second one, which we're going to cover really soon, is OLTP stream. This is for real-time transactional processing, and then it creates like a highly optimized knowledge base that our agent can query really soon. And that's why we're going to do it in CloudSQL today. And we're going to also play around with pgvector so that we can index our search and to get even faster. Ayo, why we're doing CloudSQL for this part and we're not continuing with BigQuery?
Yeah, so as you mentioned, BigQuery is meant more for OLAP workloads. So these are analytical, big data sets that take perhaps, multiple seconds, but that's the point, whereas doing very heavy transactional or analytical workloads. For something like CloudSQL, that's meant more for real-time, low-latency transactional workloads. So whether it be like bank transactions or just something that has to happen in real time. So when you think about production, if we're doing RAG in production, we want to do that against OLTP kind of database rather than an OLAP, data warehouse, just because we want real-time results, and something like CloudSQL can give that to us.
Yeah, a good example can be like if you have a customer service agent, you want to get results soon. You don't want a customer wait very long time, right? So that's why you want something have low latency, which CloudSQL can be good use case in this scenario. And let's come back to step 6 and continue. The first, let's copy this, go to our Cloud Console. This is, I need to reconnect. But usually I think if you stay here for a longer time, it's better to refresh the page because the Cloud Shell will expire every 30 minutes also. And then, so I pasted this instruction here. So here basically first you want to have this CloudSQL instance and then making sure we have this service account email and set this IAM policy. Maybe you can explain more what is a service account email and why we need this IAM config for our CloudSQL setup.
Yeah, great question. So essentially all we're doing here behind the scenes is creating the service account that's going to be the acting identity for our CloudSQL instance. And later on, what we're going to do is very similar to what we did with BigQuery, where we essentially enabled a connection service account to communicate with Gemini directly in BigQuery. We're going to do that same thing via an extension with CloudSQL. So you're going to see that coming up. So overall, long story short, so as you can see there, we're giving that service account the AI platform user role so that it can actually call, Vertex AI API such as Gemini. But yeah, again, this is going to be coming up soon.
Yeah. So next, let's go to this. You can see that we already set it up correctly. You can also go to Cloud Console IAM to check it's updating in the console. But we're not going to do that. Oh, oops. Need to, I think I accidentally copied that command in the console, just place it again. So now let's making sure to create the SQL database first. So what does behind the scene is it's creating the SQL, and this instance is this is the name of the instance. This is the project name. And the next step is let's take a look at it. You can just copy this link, or you can search CloudSQL here in the in Cloud Console, but I'm going to just copy this link and paste it to go to my CloudSQL Studio. So if you copy the link, you can see that you need to log in to your database. So making sure you follow this instruction to log in. So making sure first you select this as your database, and then you need to enter the Postgres as a user, and this is the password. So I'm going to choose this Postgres as a user and the password and authenticate. And now you can see that this is all the data it's rendering over here. And the next step is you can, in the SQL Studio query editor, paste the SQL code to enable the vector data type. So I'm just copy this. And here, this is the data. I'm currently at CloudSQL Studio, right? This is all the data over here. So right-hand side, I'm just opening a new query window. So just copy this and paste with a run. I'm going to zoom in case it's too small for you. You can see that it's successfully executing. So we have successfully creating this extension.
Yeah, the first one for being able to capture vectors within CloudSQL or store vectors, and the second extension, as mentioned before, that's going to be our extension that allows us to communicate with Gemini models and Vertex APIs behind the scenes.
Yeah, this one is Google ML integration. We're gonna see how we use them really soon. So next, we need to create this table to having all the embedding. And you can see, yeah, this is like embedding 768 because embedding model convert the text to 768 dimension over here, and this is a table for us to query from. Just copy this and paste to create this table so that we have this table available first. And then let's try to, so now in the CloudSQL, we want to use this embedding function. So this is like exactly what I mentioned before, that it's powered by the Google ML integration extension that we're creating over here. So it allows us to call warehouse AI embedding model directly from SQL query without actually loading the model. It's calling our warehouse AI model. So let's copy this and see what is the result. Did I copy the wrong thing? I guess. Let's just copy this again, making sure.
So essentially, we're inserting a row into the database. Is that correct?
Yeah.
Yeah.
So here we are using text embedding 005, this model. And then this is our current setting. And now let's verify the query. I'm going to open a new tab and paste it. Verify by selecting this so that you can see we have this embedding preview over here. This is the preview of this scroll content. And now let's so we have this embedding, and previously in BigQuery we do like a similarity search by call sign, but here we do something even more advanced. Is we want to do like HNSW index so that we can quickly find the results. And here is the HNSW concept. Basically, we are at each layer we can like instead of just search everything in the embedding space, we can just get embedding and go to that area and do the traverse to find the related data. Yeah, sorry.
One way I thought it is like think about vector search as trying to find like let's say you're looking for like a blue sweater and you have a closet that you have to kind of search for everything. It could take some time. You know what you're looking for, but it's going to take some time. Essentially, what hierarchical navigable small world is doing is it's pre-indexing your vectors so they're easier to find. So think about like color coordinating your closet. So now you have all your blues in one place, you have all your pinks in one place. So now if you're looking for a blue sweater, you can just go directly to that place in your closet, and it's a lot faster to find. So you tend to see faster results when you have HNSW indexing involved.
Yeah, so you do not have to do brute force search to search everything in that database because you're being indexed this by color. So how we're gonna do our search right now is we're gonna just normal search first, and then we're gonna add this create this index which HNSW which Ayo just explained like how. And then like we're gonna run it again and compare how much faster it is using when we're creating the index. So let's give a try. So first, let's just do a normal search. First, without using index, basically here you're just searching, do a brute force search, like search everything in your embedding space. I'm just gonna copy and paste it here, and then you can see. This is a query plan, and this is execution. This is the planning time, and this is execution time.
Yeah, so it's about 0.4 seconds. Yeah. So overall, what we're going to expect is that once we add the HNSW index, it should be a lot faster. So we'll see how much.
Let's see. So this is exactly how we are creating the index by having this create index on HN using HNSW. And it basically has an embedding vector called sign ops. So let's copy this. And I'm going to create a new tab and paste it. So you can see statement executed successfully. And next, let's try run this again. I'm going to copy this and then to a new tab and run this again. So you can see that the execution time now is 0.2 versus the execution time was 1.4 at the very beginning. After running the index, creating the index, the execution time is a lot faster because it's not searching every single thing. Like instead, it will finding the index and go to that area and then do the search. Yeah, cool. So now we just covered how to create an index to quickly do the search in CloudSQL. So far, we've done RAG in BigQuery, RAG in CloudSQL, and we even play around with index to quickly find the thing in CloudSQL. But what if in a real life scenario, like we have so many data, we have new data coming out every day, right? How do you scale this case? Like, for example, if you have new data, do you just manually put everything to CloudSQL and like start to do this RAG again? Like, how do we really automate the whole thing? How do we really scale in this use case? Right, Ayo?
Exactly, yeah. So how do you scale? And I guess the answer is something like, it's just one answer. There's different ways you can do it. But what we're not going to cover is how can you scale this using something like Apache Beam and Cloud Dataflow and Google Cloud.
Yeah, can you explain this?
Yeah, so Apache Beam is essentially a workflow engine that you can run on different platforms. On Google Cloud, you can run it on Cloud Dataflow, which is a managed service that we have. And essentially, it allows you to automate multiple steps. So you can run this as part of a batch pipeline or a scheduled pipeline. What we're now going to do is essentially automate the RAG pipeline that we just built earlier, both in BigQuery and CloudSQL, and we're going to essentially program it as part of a Cloud Dataflow pipeline. So everything from the extraction of the text to the chunking to the embeddings is all essentially programmed, and then we're going to have CloudSQL as a sink. So essentially, you could have multiple files coming in per second or per minute. Something such as this Dataflow pipeline could essentially process all those files and then have it, essentially ingested into CloudSQL so that your RAG agent, which we're going to build afterwards, can essentially have access to real-time information.
Yeah. So let's take a look at how do we do that with Apache Beam in CloudSQL to automate the whole process so that we don't have to manually do the process ourselves when we have more data or when we want to scale them in production. So first, let's copy this to Cloud Console. Just go to Cloud Console. Here, let me clear the window.
And essentially, one thing I've mentioned is that essentially when you're running a Cloud Dataflow pipeline, it's essentially VMs that are running behind the scenes, and these VMs can run container images. So if you want to have any custom libraries or Python packages pre-installed, essentially you would have a pre-made container image. So all we're doing here is creating a container image ahead of time that our VMs as part of our Dataflow pipeline or machines are going to use. So you don't have to worry about any packages such as Google Cloud Storage, XYZ being missing from the actual machine image.
Yeah, I'm going to try search this Cloud YAML file. So I just open everything in this new window and look for this file. And this is exactly like I mentioned that we want to have the container image. I don't think it's this file, right? I think it's
That's the agent one, yeah.
It's a pipeline one, yeah. So this is it should be on the pipeline that we have this image have the cloud shell in the cloud built to store the final forged registry route, and this is the things we try to deploy. I'm gonna close this, and the next step is to activate the environment. To see the deployment process, as always, you can go to Google Cloud Console. I search Google Cloud Console, and here when we do a search, I search Cloud Build, and this is currently running. So it's not a black box. Oh, okay. Here you can see all the process. It's trying to push the image. Okay, let's take a look at our deployment process. Let's see it's building successfully. And here is success, and we can continue to the next step, which is activate our environment. So here we're using requirement.txt to have our dependency and making sure we are install all the dependency and activate our virtual environment so that we can do all the process in a controlled environment. And now I'm going to go to this console and then just paste this and waiting for it to install all the dependency and activate the environment. And while we're waiting for the installing, we can take a look at what's next. So next step is, remember I was just explaining this Apache Beam and Dataflow. So this is, now we are going to create this automate pipeline so that we do not have to manually every time generate embedding ourselves. This is exactly how we're going to scale them with Apache Beam. And so we need to go to this file like pipeline/inscribe essence pipeline.python file first to create our embedding model. So this is, does this look familiar to you? Like we're having this embedding model, we have this.
Yeah, it looks familiar to the code that we had with BigQuery when we were establishing the connection with the embedding model, ML-generated embedding. It also looks familiar to what we did in CloudSQL, where again we established an extension with the Google ML integrations, and we're able to generate embeddings.
Yeah, so previously we tried generate embedding in BigQuery and CloudSQL, and this is how you generate with pipeline Python code. At first, I'll copy this file name so that I can go to this file. Oh, it's still installed the dependency. I'm gonna wait. All right, you can see we have activated our environment, and it has this env at the very beginning. That means you have successfully activated the environment, and it's point to the right project. And I'm making sure I copy this file name and go to in my editor. I will try to find this file. This is inscribe essence pipeline file, and look for this comment. Replace embedding logic. First, let's create this embedding model. And because this is Python file, making sure you be careful with the indentation. And this is like a text embedding 005 that similar to the logic. We are creating the embedding in BigQuery, but here we're creating them in this pipeline file. And next step is let's actually define what does the process look like, because we want to automate the process, right? We want to like scale them, but what is the process we want to automate? And here is how we define them. And let's first look for this replace me read file. So the process is first you need to so for whatever new file you want to ingest to this pipeline, you need to first read the file and read the match, and then extract the related content so that later on you can create embedding and do the vector search, right? So the first process is you need to read the file first and read the match, and mapping the file to extract the related content. And just copy this and replace. I'm gonna replace this way so that it's in the right indentation. So now I have successfully read the file. So that every time you have the new file, it will processing this for you. And once you have this extracted, the next step is you want to generate embedding.
Yeah.
So, yeah, Ayo, anything you want to add?
And it's, you mentioned we're doing it in batches. So pretty much all we're doing is we're grabbing up to 2 scrolls at a time, and embedding the batch.
Yeah,
And we also have different outputs as well in case anything fails. You can put that into an outputs failed kind of a pathway.
So this is for error handling to have a more robust pipeline setup. Next step is once we get the embedding, we want to write to the database. So just copy this and paste to the database part. So basically now, whatever you upload first, it will extract the related information and generate the embedding, and then write the embedding, processing that, and write to the database. This is name. And next is we want to replace this for replace me log failure. This is like I mentioned that if we have a failure case, we will have this log information, so that this is for like error handling, so that we know what is going wrong. Anything to add?
Yeah, and again, as you can see, for the failure case, we have embeddings.failed. For the process, we have embeddings.process. So again, error handling, but Dataflow has really nice syntax that allows you to essentially grab the outputs from each of the pathways and kind of do separate processing with them. So that's kind of the underlying syntax as well.
So with this pipeline setup, you do not have to manually generate embedding every single time, because we will automate the thing for you with this pipeline. And this is exactly how you define the workflow. The next step is let's run this file. So here, what we're doing here is first we're making sure we add the environment, like we activate the virtual environment, and making sure the environment variable is set up correctly. And then we want to run this Python file we just created, right? So we just create this pipeline before we want to run this. And Ayo, why don't you walk us through all those necessary parameters here? That anything we need to pay attention to.
Yeah, so when you build a Dataflow pipeline, the actual pipeline building can take a little bit of time. There's a staging location for any intermediate files that's generated during that process. The SDK container image, essentially that Beam package. If you scroll to the right, you can kind of see which version we're using. I think we're using the latest. That's great. And then, as you can see, as part of the input pattern, if you recall, the first step of the pipeline is we want to filter and only grab the files that we care about from the bucket. So essentially, that's our input pattern. And then the project and job name, those are all kind of custom to you. But that's essentially what we're designing here. So we're about to run it, and as you're going to see, it's going to take a little bit of time for the pipeline to kind of kick up. But once it's kicked up, it's pretty fast with how it processes the files.
Yeah, I just copy this to the console. Here, if usually we have this region to be US central one, but you can also try a different region to find a region that's closer to you. If you see that we have the resource pool exhausted, it might be because we have the low temporary constraint for the selected region. And we can waiting for this data flow to create it. I'm gonna copy this and wait for the data flow. So right now, if I copy this, currently I'm at Dataflow Google Cloud Console, and this is our pipeline. I'm just copy this. You can see that it's currently running, And this is exactly what we just defined, right? We start from match file, and then we want to read the match to extract the content. This is exactly what we defined over here: match file, read match, and extract the content. So that now every time whatever you upload, you will extract the related content. And next step is you will distill the patch with the embedding, and then create an embedding to the write to the spelling book, and if it failed, it will log the failure. And here is how we're processing them: is we have this, we dispatch it to the field and processed, and with the processed, we are processing them right into the database, and if it fail, it will create this log. So this is exactly how we define in the pipeline, and we're waiting for them to finish.
Yeah. So again, it's going to take about 3 to 4 minutes in this particular case. But the nice thing about Apache Beam and Cloud Dataflow is that, as mentioned before, you can use it in a stream processing workflow. So while it may take a few minutes for the initial pipeline to kick up, if you're using something like a stream processing workflow, essentially it runs continuously. You can set min workers, max workers. So let's say you have 1 million files come in at once. The pipeline is going to scale to as many workers as you allow it to scale to. If you only have 5 files coming in per minute or something like that, and it only needs 1 worker, the pipeline is going to scale down. So overall, after the initial buildup of the pipeline, it's pretty quick, and you can kind of set the limits of how much you want it to scale.
Is that here, like a min patch file and a max patch?
I know that's slightly different. So great question. So if you want to set the how the pipeline scales, there is a separate kind of parameters that you provide as part of the runner configuration for Cloud Dataflow. So it would actually be in this location here where you would it's actually min worker, max worker, and you can do that as well. Yeah.
But here we don't have this configured over here.
Yeah.
But we can put this in on the screen right now so that you know how to scale them.
You can also take a look at the Dataflow pipeline. We can see how many workers we're using right now. So if you scroll down on the right side, you can see that we're using 0 workers currently, a little bit higher. So right there, so our pipeline is still scaling up. So you can see it's starting to pull 1 worker. So as mentioned before, it can be a little slow the first time the pipeline kicks up. But once it's kicked up, you could have it running continuously. There's no buildup after that, or it could be batch workflow. And if it's a batch workflow, each time it kind of kicks up the batch, it will be a little bit slow. But again, it comes down to your use case. Do you need real-time processing, or do you need more batch, workloads processing?
Yeah, when do you think is a good use case for real-time processing in the industry?
Great question. I will say if you're building a RAG agent, for example, and you truly need real-time information. So let's say it's like a customer service agent, going back to what you mentioned earlier. And let's say this customer service agent is working as the receptionist at a hospital. And it's very important that this agent has real-time information about each patient. So let's say I want to be able to ask the agent, tell me more about the room or the current status of this particular patient. I'm hoping that it has access to all the real-time information that's been logged from the most recent, visits by the nurse and doctor. So that's more like a medical use case, but you can imagine it being very important to have RAG and retrieval of all the most relevant information as it is now. But something that's more batch related, maybe something like something that doesn't change often. So let's say it's more like a retail use case where let's say
e-commerce.
E-commerce. Let's say you only change the product description of a product every quarter or every 2 weeks. Then you don't really have to have a streaming workflow. You could have essentially a scheduled weekend pull the most recent product descriptions and update the database with that. So again, it comes down to your use case in the industry as well.
Yeah, that makes sense. Thanks for explaining the use case.
No problem. Okay, oh no, we failed. So let's see what happened.
So I think if it's failed, that probably means the region. We want to exhaust the region.
Yeah, so let's see.
Let's take a look. Let me close the job.
Yes.
So now we can see that we have this zone resource pool exhausted. This is exactly the error we mentioned over here. So it might be because temporary resource constraint. So maybe we can replace the region to be one of the region below. So I'm gonna try to replace it. So I'm gonna just I'm gonna end the process. And I'm gonna copy this. So for the region, where is the region? Okay.
You may have to repaste it. I think you lost your place.
Okay. I'm gonna clear the window and I'm gonna copy this. How about I just copy this? I'm gonna just copy this until the region so that I can just manually define the region.
Okay.
Oops. Region equal to maybe I do a South America.
Okay.
Okay, let's give it a try.
Okay.
I'll refresh this. Go to the overview, monitoring, the job. Okay, so you can see that previously the job failed, and this is a new one. We just kick off.
Yeah. So again, it's going to take another a few minutes, but within 4 minutes, you should have a good understanding if it worked or if it failed. And if it failed, it's most likely due to a resource issue that Annie just demonstrated how to kind of bypass. So make sure you update the region. But yeah, we'll just give it a few more minutes for this run to complete.
Yeah, so looks like it finished. Once we change this region, great. So now we can run this command like a SQL to verify it. So just copy this and go to our CloudSQL Studio and just select this and paste it. And now we can see that current count for HNSW is 4. Is that accurate?
Yeah, accurate. So we've now essentially our Dataflow pipeline ran. It grabbed the files from GCS, transformed them, and loaded them into the CloudSQL DB. If you remember before, I believe you only had one row that was manually created. So this is a good sign. Yeah.
Yeah. So next is trying to verify the embedding. So just similarly copy this and paste it to see the embedding. That's now you can see that with data pipeline, it's able to we do not manually create put any uploading any creating the embedding. It will automatically creating this for me while after this data pipeline process, right? So now we have this data pipeline. We know how to quickly do the search with index in CloudSQL. We create a data pipeline so that it will automate the whole process and it allow us to scale easily and for all the different type of industry use case like Ayo mentioned. And next is how do we connect that to our ADK agent so that we have this agent able to do the similarity search and do the RAG. So now, finally, I'm going to our agent code. So the agent code located as agentwords-data engineer/scholar/agent.python file. So again, in this editor view, I'm going to search for the agent file. And let's take a look at this agent we are trying to do so far. So here we need to copy this replace convert embedding, which is over here. And replace this with the result. So I replace this with the result. And let's take a look at this is what we just replaced. Oh, by the way, making sure you're be careful with the indentation for the Python code. So now we are creating a tool for agent to use. Basically, agent with a model as a brain and is a tool in the toolbox. So model gonna do reasoning to see which tool I'm gonna use to solve the problem. So whenever user asks a question like, do the search for the document, and then agent can choose to using one search tool, and then the search tool will do the search in the database. So like agent using the model as a brain and then to search from the toolbox. So whenever you ask a question, for example, search what is a monster, what are the skills you want to do the search, and then agent gonna using Gemini as a model to decide, okay, I'm gonna using a tool to solve this problem, and then the tool can be maybe this lookup tool. And this is how why so in the lookup tool we want to have that RAG like similarity search. So here you can see that we are using this embedding model. This is the embedding we're just creating, and we generate the embedding list and then to connect the database to do the RAG retrieval. So this is our retrieval. So we're creating this tool to do the retrieval from the database. And next is we want to find replace the comment, replace RAG retrieve. Here, copy this. Here you can see that we want to executing this, like selecting this from the order by the embedding. So this is basically a similar process we just run in the CloudSQL, that we create the embedding, we have the embedding list, and we want to do the search, and then we want to do the top 3 search. Right, Ayo?
Exactly. Yeah. So essentially, we're just grabbing the top nearest neighbors from that vector search behind the scenes.
Yeah. And the next one is trying to find replace call RAG. Just copy this. And here is where we're creating our agent. So just replace. Finally, create our agent.
Yeah.
So you can see the agent, we are using LM agent. So that the model is 2.5 Flash, and the name is Scholar Agent. So this name is actually very important because it's not only for human to read, it's also for other agent to understand what is an agent. And also, if you want to deploy agent to agent engine, you also read this by this name, right, Ayo?
Exactly. Yeah. So it's going to look at the name. It's also going to look at the description of the agent if it's provided.
And here we are providing this tool. This tool is exactly the tool we just created before, right? So we implement this tool that is generate embedding and do the similarity search, connecting to the database. And here for this agent, when we are asking the scholar question like, you want to do the search, and then so the agent will, based on this instruction, consult this using this tool for the information for the specific monster. And then you will use this the tool we just created and look up in the in the database. And for the actual lookup, we're doing the search with vector database. That's how we're creating the RAG agent. So now we finish the RAG agent. We just do the ADK run to test the agent we just created. So here we go to this folder and we activate the environment just to making sure that the environment is the same. And the ADK run is basically we are running the testing the agent in the command.
Yeah, so ADK run essentially brings up like an interactive terminal interface that you can prompt your agent, get example responses from it. It's a good thing to do before you deploy your agent. So we always recommend before you deploy your agents, always test them locally. The nice thing about the ADK, it has different ways you can do it. You can do ADK web, which is more development UI approach, where you can do evaluations. You can kind of see the actual chat outputs directly on the screen. So there's a lot you can do from like a local testing standpoint.
Yeah, do you like ADK web or ADK run? I like ADK web because it's more like visual, and you can also see all the tracing, and you can like evaluating them.
Yeah, personally, I like ADK web because it's just more extensible. So if you want to do multimodal inputs, you can just upload a photo. ADK web handles like the image transferred directly to the agent. As far as like ADK run, it's just more text interface, but it has its purpose. So
yeah, but it's quick. It's more reliable, I feel. than ADK web.
Potentially. So,
So now we. Oh, sorry.
no, I was going to say, let's prompt our agent and see what it says.
Sure. Let's say, so we want to ask the agent this question, and then we expect the agent, given this user's input, and based on the instruction, using our tool we just created, do the vector search. And this is how we want to build the RAG agent, and we want to test the RAG agent. So just we've been trapped by Hydra of scope creep. Pretty cut off.
Yeah. So a lot of these monsters again are like monsters that hinder development productivity. So we talked about dogma in episode 1, talked about procrastination, now scope creep. But yeah, let's see. So behind the scenes, what we're expecting is that we should see our agent call the tool, and ideally from the tool we get useful information back, and then we can use that as part of our response to the monster.
Yeah. Okay, so if you see this arrow, that probably means you need to refresh your page.
Yeah, so it's a good error to get. It's not a good one, but I'm happy that we got it. So essentially, whenever you see that error, it just means you have to refresh because your terminal lost authentication status.
Yeah, Ayo, actually, I want to give a try about the ADK web.
Oh, sure. What's
so that we can see the process. Let's give it a try. Okay, so you can see that it launched on this endpoint. And let's select the agent. Scala, I think. So let's ask this question. Hopefully we can see what tool is being used. Yeah, you can see it's using this tool we just created. Grimo lookup tool. And this is like how we're implemented before, the tool we implemented. This is the response from the tool. And this is the final result.
Perfect. So the RAG process is working really well. As you saw, if you click the lightning symbol tool sign, the first one on the right hand side, you can actually see what was passed to the model. So or to the function Hydra scope creep. So if you remember when we created that function, essentially what it takes as input is the monster name, and it then does RAG against that. So it looks like that's working. Yeah.
Yeah, so this is the function we just created. Here we took the monster as a name, and this is the result. So this is exactly we see over here. Cool. And next step, once we know this is working, we need to deploy things to Cloud Run so that we can eventually fight a boss with agent-to-agent protocol. So let's copy this and end the process and paste it over here. So if you're curious about, what is the agent-to-agent protocol, we talked a lot about it last weekend. So you can go to episode 2 that we talk a lot about agent-to-agent protocol. Essentially, we are once we deploy the agent, we need to figure out a way to communicate with the agent, and we want to have the agent card that demonstrate like how to talk to this agent, what is the agent good at, what are the agent skills, and then what is the connection type, and then like based on the protocol, you can just easily connect into that agent and using that agent. So yeah, Ayo, anything you want to add at this point while I'm waiting for?
That was a good summary. Yeah. So A2A is good for use cases where you have to bypass, cross-organizational boundaries. So it's nice to build local agent teams when all agents can be deployed on the same runtime. But imagine a use case where you have one person from your billing department has their own agent, another team from your finance department has their own agent, and they're all kind of managing their agents separately. How can you kind of allow these agents to communicate without them being on the same runtime? A2A solves that problem. But again, if you want to know more about A2A, head over to our first episode.
Second.
Second
episode.
Oh yeah, first episode, but part 2. Yeah.
Yes.
Yeah.
Great. Yeah, I think what you explaining is mostly like remote agent, right? So one basically you want to have like so the deployment strategy we have is you deploy single agent to different cloud run, and then you communicate with them. Another deployment strategy can be you have like a multi-agent system. You deploy the whole multi-agent team to Cloud Run so that they're you just only have one like Cloud Run instance for it. But in that
Yeah.
case, just like what you mentioned, if you have a different team, they cannot work on it separately, right? So it's not easily for like scaling for team to work together, but it's easier deployment because you just need to deploy them once. But it's like decoupled, so it's not easy to scale and to manage to maintain. So it's like a trade-off for the deployment strategy, from my point of view.
Okay. Yeah. No, that's I agree.
Yeah.
Yeah.
Because sometimes if you just want to have an MVP version or you want to have like a demo, you don't have like many people in your team. You don't
Yeah.
necessarily want
Scale.
to. Yeah, it costs more, right?
Yeah.
And also it's more complicated because you set up the A2A protocol versus, for example, if you just want to have like one agent deployed or like a whole team deployed to Cloud Run or even like whole backend service deployed, that way it's easier for deployment and to the setup. But however, it's harder for you to maintain, modify, manage across team, and then scale, right? So I think it's really a choice. Like it's a design choice for you when you think about the deployment strategy.
No,
And
I agree. And another design consideration that I'm interested to get your opinion on this is
yeah,
latency. When would you perhaps not do A2A or not avoid A2A because of latency? Yeah. Network
for
between agents. Yeah.
example, like streaming.
Yeah. I would say you want to minimize, network, communication between agents. If you have local agents, they're on the same runtime. So there's less HTTP, connection, latency that could happen, but obviously it's less scalable perhaps that way. What are your thoughts?
Yeah, that is a good call. So for example, for example, we want to have like multi-agent doing the streaming or like for example, they have to um, like for the use case, like we have the multimodal use case. Maybe um, we have to like pull the data every second or so.
Yeah.
Maybe it's good to consider the local, like maybe we want to put them together to reduce the latency so that we can pull in the data faster for the live use case. What do you think? I'm just brainstorm.
No. I think, yeah, like you said, I don't think there's any right or wrong answer. It just comes down to the specifics of your use case and what you're trying to optimize for. If you're trying to optimize for scale, A2A could be a good answer. If you're trying to optimize for, really low speed or latency, perhaps local teams might be the best approach depending on your use case. But again, A2A doesn't add so much latency, but it does add network constraints that you have to kind of think about a bit.
Yeah,
Yeah,
that's a good call. Every day I'm learning a lot from you, Io.
same here. Same here.
You're just know everything. Okay, let's take a look at our build process. Uh, build. Oh, it's deployed successful.
Yay.
Great. So now we're ready for our boss fight. Let's just copy this.
Fighting a boss in the cloud is what we've been building up for. But now we have a RAG agent. It's deployed on Cloud Run. It's on its own endpoint. And if you recall, the boss is its own agent as well. So when we're fighting this boss, it's really A2A behind the scenes. That's facilitating the communication.
Yeah.
So let's go ahead and do it.
So we're gonna run those two command just to get the URL, or you can get them at Cloud Run if you
Yeah.
want. So here's the one for Dungeon, and that is the one for Scholar agent. So if you open the Dungeon one, you will have this battle. And let's enter it. And here you need to put your, I think you need to put your URL here. This is the A2A endpoint. You're a scholar. Your opponent is
Obfuscation.
how to say that?
Obfuscation.
Obfuscation. Thank you.
Okay,
are you ready to start a fight, Ayo?
I'm ready. I'm super ready.
Okay, let's start. Clarity for junior developers.
The truth is layers and direction. Yeah, so as you know, all villains like to talk. So we have to give our monster some time to give his evil kind of, but overall he's done. So
yeah. So what does the task type equal to retrieval parameter do when creating the embedding?
I think the second one. It optimizes the generated embedded vectors for retrieval.
Yeah.
Yeah, that works. Okay.
Why is it important for vector in PostgreSQL the table to have the same dimension as the embedding model's output? Because the dimension.
So whenever you're doing RAG, it's a common source of error is when people embed their database in a different dimensionality than what they're querying in. And oftentimes that just won't work. And it's also important that even if you have the same dimensions, that you use the same models, because sometimes, different semantic meanings get different encoded in different ways. So you may be retrieving answers that aren't really the top nearest matches of what you're expecting. So it's always good to make sure that you're encoding your DB and the query in the same dimensionality. And we recommend the same model as well, just for best performance.
Always learning a lot from you. And the next turn is, in the RAG process, what happens during the retrieve step? So I think it's the user security is converted to the vector.
Yeah, I think that's so too.
It's basically the foundation of similarity search.
Exactly, yeah. And it looks like the second answer has been correct most of the time.
Should we choose a second again?
So
what does
this first one, so we can choose the second one again. Yeah.
Yeah, to do when creating embedding.
Okay, it looks like one more, and we're good to go.
Is the second one?
The second one, yeah.
Is the second one again for the last question?
Let's see. We may need to improve this random generator. In the right one, what happens during
the same one? The same one. It's the second one.
Okay, but it's obfuscation. Yay!
We fight the boss. Congratulations. For those who watched it now. All right, let's do a quick recap of what we covered so far. So last episode we covered how to do RAG in BigQuery, and we covered how to do the ELT, extraction, load, and transformation, right? In BigQuery. And today we cover how to do RAG in BigQuery and how to do RAG in CloudSQL. And not only that, we create this pipeline to automate the whole process so you can easily scale for like a large, use case in like for a massive data in the real production use case. And we also create an agent so that you can using agent to smartly search in vector database. And Ayo, anything to add?
Oh yeah, so that was a big journey. Thank you for staying with us.
Yeah, thank you.
We'll be back next week. But until next time, I'm Ayo.
I'm Annie. Thank you so much for watching this episode. See you. Bye.